Hi everyone, welcome and thank you for watching us. As you already heard, my name is Denis and I will be talking today about magnetic force microscopy and how to do it with Nanosurf AFM systems. Now, what exactly is magnetic force microscopy and why would you need it? Well, it's rather obvious. If you have a magnetic material or a thin film of magnetic material on a surface, or you have a magnetic nanostructure, and you would like to know the local polarization of your magnetic dipoles or configuration of magnetic domains. So all these magnetic signals that you would like to visualize, so then you need some sort of a magnetic imaging technique. And MFM is one of the very straightforward techniques. It can be done in ambient conditions, doesn't need any special sample preparation, you don't need vacuum, low temperature, none of that is necessary. So here you have an example of a spin ice system imaged with MFM. On the left, you see the topography. So these yellow dots or rectangular structures are magnetic. And on the right, you see the MFM signal. So what it shows you that, all these magnetic rectangles, they have a different dipole polarization. So in different places, you can see there is a different magnetic configuration. So the MFM is measuring magnetic interaction between the local magnetic field and the magnetic tip. So to understand a little bit how the MFM is done, so we have a cantilever with a magnetic coating on it, and this cantilever is shaken with the piezo. And we're measuring the oscillation of this cantilever in amplitude and phase. And we're looking at the phase contrast. So we're looking at the phase contrast because phase varies monotonic with force. So it's a very convenient quantity to measure the force. And also in magnetic measurements, you have could have a different forces, attractive and repulsive. So you have different sign of the force. And this different sign of the force would give you the same amplitude. So you will not see the contrast. But however, the phase will give you different, will have different effect by this force. So this is why we're measuring it in the phase contrast. So just to elaborate it a bit further, how the magnetic contrast is built. On this slide, from left to right, we have three different scenarios. In the scenario number one, the dipole in the cantilever is aligned with your local magnetic field, and then you have an attractive force. So the attractive force you see here on the right will result in the lower frequency of the cantilever, and that would mean you have a negative phase shift. So negative phase shift will be shown as a dark color in our imaging software. A second situation is when the dipole of your tip is anti-parallel to the local magnetic field. So in that case, you see that it's a repulsive force. Repulsive force would mean a higher frequency, positive phase shift, and that will be shown as a brighter color in our measurement software. And the third option is that the field in the tip has zero projection on your local magnetic field, so they're orthogonal to each other, no parallel. So you will see no phase shift, and the color will be, well, grayish or intermediate color. So now that we understand how the image is formed in MFM, let's look at different MFM modes. Now, if you measure MFM in the contact mode, and you would like to see a phase, you will have a mixture of signal. You would have your MFM signal, but also you will have a signal that's coming from measuring the topography. Depending on what kind of material in the surface, depending on the tip, so you might get higher or smaller phase contribution from the topography, and that you would like to avoid. So there are two ways to avoid in this contribution. One is to doing so-called constant height mode imaging. Essentially, what the system does, it finds the surface in the beginning of the scan line, By lowering the tip down to the surface, it sees, okay, we have reached the set point. Then we lift the cantilever a certain height above the surface, and the tip will follow the slope that you have to find before you start doing MFM imaging. So first you find the slope, then you start this constant height mode. And in the end of the scan line, it will again find the surface and then lift up again and follow the slope back. So this technique is very convenient if you want to do fast imaging, and it works very well on flat samples. So in flat samples, this slope you know relatively well. There is no rich topography, so the distance between the tip and the sample will be the same at every point. Another advantage that you don't touch the sample with your tip at this in this mode, so you have very little tip wear, so you can use the same tip for longer. And also when you take a measurement and then you made some simulation in your micromagnetic package or other simulations, so you want to compare the measurement with the simulation, it's easier if you have a data from this constant height mode. But as I said, it works only for the flat samples. If you have a pattern and the height of your pattern is significant, say some tens of nanometers, or sometimes you get even hundreds of nanometers. So this mode will not work because you don't really know where you're landing, and also it will not be a constant height, right? So between two different points in the same sample, you might have difference in tens of hundreds or hundreds of nanometers. So in that case, we suggest using contour following mode. And that is a bit of a longer measurement because it measures the sample twice. The first measurement is your topography measurement. So the tip is following the topography of your sample and records it in the memory. And then the system would lift this lift distance, and then will follow this measured contour and keep the distance to the surface below constant. So in the contour following mode, yeah, it takes double the time of the constant height mode. Advantage is that you get a better understanding if you measure in rough samples, so you have less, of the imaging artifacts. But yeah, it is slower. It is slower, and you have a bit more tip wear. So today we will learn how to do these two different modes of measurement. Now to see how this works a bit in practice. So if, as you know or remember probably from your physics classes, that magnetic interaction is a long-range interaction. It decays 1 over r cube, where r is the distance between the tip and the sample. And so this you can clearly see on this image on the top left corner. There, we imaged first at 100 nanometers, then let's say some 50 nanometer to the sample, 20 and 15, and you see there's quite some contrast between 100 nanometer and 20. So the signal increases substantially, but there is no strong increase in the signal quality between 20 and 15 nanometers, for example. And what happens if you measure too close to the sample? So in fact, you don't gain much of a signal, magnetic signal, but what you start having a contribution from the topography. So that is a topography image on the tile right bottom tile. This is the topography, and on the top right tile, here in this white rectangle, you see there is a mix of topography and the magnetic image. So to avoid that, you do a series of images or lines, same as we did here, and you find the closest distance where you still don't have this contribution from the topography. So this is how you do it in practice. Another question is that we're often asked what kind of tip to choose for your measurement. So essentially, there is only two choices you can make, or three choices. So there's a hard magnetic coating with high coercivity, and then the soft magnetic coating with low coercivity. And sometimes you manage to get something in between of these two. So what does it mean? So in the beginning, if you don't know your sample, I would always go for the hard coating. It means that the interaction between your tip and the sample is high, so you get high signal to noise. But it means that you also have a higher chance to modify the local magnetization in your sample. So if you might get, in certain samples, you will see some artifacts that are caused by the tip. So if you start seeing these artifacts, then either you should lift your tip a little bit higher, so to decrease this interaction. Of course, you will lose XY resolution doing that. Or if you don't want to lose your XY resolution, so then you change to a tip with a soft coating. So soft coating, low interaction between the tip and the sample, a lower signal to noise, so the image quality will be less, but at least you will not see the artifacts that are caused by the hard coating tips. So in the way it looks like or works in reality, I found these two images on the ResearchGate. So the researcher here was studying 60 nanometer nickel film deposited on silicon with a hard tip and with a soft tip. And in both cases, he used 20 nanometer lift of the tip above the surface. So you see already on the left image that is made with a hard tip, the signal to noise is pretty good. So the phase difference between the dark region and the bright region is about 8 degrees. So that is a very significant phase difference in MFM. But you also see there are these imaging artifacts. So his domains, the main structure is being affected by the tip. So the domains are moving. It's not a stable situation for the imaging. Now, after the researcher changed to a soft metal, soft magnetic material tip, so you see the signal to noise got worse. So the phase difference is only 1.4 degrees. On the image that we would be doing today, we will try to keep phase delta phase 2 to 3 degrees, maybe 4. But so certainly we would not go to 8 degrees. So there in this right image, you don't see any artifacts, but yeah, it's a bit noisier, but at least you have the structure of your domains and you preserve your XY resolution. So the thing to take home is that you have to choose your tip according to the sample. So there is no universal recipe. And even depending on the thickness of your metal, sometimes it will work with a hard tip, and then you change the thickness, and then you see that you have to use a thinner tip. Softer tip, right? So there's two tips that we consider standard tips for our software. So you can find them in the catalog of our, not catalog, in the tip settings. So these are hard coded or programmed. So they're there. One is a magnetic multi-75G tip from budget sensors. That is a hard magnetic tip, and as far as I know, this is the only one magnetic tip from budget sensors. If you need more variability or variety of these tip materials or tip or coating thicknesses, so you could use MR probes from nanosensors. So then they have, I think, about 4 models with different coatings, different thickness of coating, and also different tip shape. And tip shape might be important if you would like to do a high resolution magnetic imaging. So the way it works, if you look in the literature, so the ideal shape of the MFM tip for high resolution imaging is a long, narrow cylinder. So the reason for that is that, well, we already said that magnetic forces are long range forces. It means when you do the imaging with the MFM tip, not just the very tip, the end of it, the sharp pointy part of the tip is participating in the imaging, but some of the volume or the surface of the tip above this pointy part. And the way this volume is shaped, and how much material is on this part, it will affect your XY resolution. So essentially, here's the comparison from nanosensors they did for the different tip types and different tip shapes. So these 3, I would say they're pretty much the same shape, but one of them is this triple S MFMR tip is very narrow and long tip. And you see this gives you the best lateral resolution. However, if your features are large and you want to scan really fast, there is really no need to go for the smallest possible tip. You see, I think until 60 or 50 nanometer feature size, these 3 tips are doing just fine. So these have difference only in the magnetic coating. And only if you have to push your resolution down to 30 nanometers, only then you would start using this the special SSS MFMR tip. So here, again, the moral is if you measure in large structures, so don't try to get the best or the most expensive tip. So you're going to be just fine with your standard. And even the tip that is used and a bit scratched magnetic coating on the tip of it is probably going to give you the same results as the very new tip. So there's no need to change tips very often. Okay, so moving to today's experiment. Today we're going to be measuring one of our demonstration kits. It's a magnetic tape with some information encoded in it. So the magnetic image would look like this. So it's just some domains that basically mean encoded information on this tape. So the sample is very flat, and even though we're going to do it with the constant height mode and in the contour following mode, so these 2 images would really look the same because the system would essentially do the same thing. But for the demonstration, I will show you how to do both of them. Okay, so let's start. I'm going to show you now how the system looks like. Well, you saw it already in the beginning of the webinar. So now this is the CoreAFM. So for the magnetic imaging, you would use conducting sample holder. So this disc, and you would ground it. So this is, if you can see, this is a grounding wire to avoid any electrostatic interaction between the sample and the cantilever. So you only have magnetic interaction. So that's pretty much it. I'm going to close it. And I'm going to close the acoustic enclosure, so we don't have any noise. And I'm going to switch back the camera. So you see my face instead of the black box. And we go back to the Nanosurf imaging software. Okay, so this on the left, you see there's a cantilever, there is a sample below, there's a laser spot on the cantilever. I already did the laser alignment, so we're not gonna do that. But what you need to check that you're doing phase contrast measurement. So this is where will be our magnetic signal, and you're using the right cantilever. So in this case, I'm using this multi-75 mg from budget sensors. So the next step you need to do, you need to characterize your sample and measure its topography. And before you do that, you need to find the vibrational frequency of your cantilever. So I did that already, but just so you know, when you do the magnetic imaging, you would like to be at the top of the resonance. So this is your set point, and this set point, your phase is nice and linear with the frequency change. And if you configure your sweeper, so you have 0 amplitude reduction, and it doesn't really matter which sideband you're going to use because you're on top anyway. Okay, so let's find vibrational frequency again, just to see how it works. All right, so this is done. Press OK. And we can press approach. So you can see there's a shadow of the cantilever on the sample. So there's quite some distance. So just press approach. And the system will again tune the vibrational frequency, just not plot it for you. Okay, here you can see the system is moving. So the Z stage is moving. You can see it at the bottom on the left. There's a green progress bar. And on the right, you can see the distance between the shadow and the cantilever is getting smaller. And they're almost overlapping. And when the cantilever is sensing the surface, it means that the approach is done. Okay, so the approach is done, and the first thing we should do, we should see what kind of topography we have. I already looked at it, but okay, let's do it together. So maybe increase a bit the set point. So essentially the set point was too low and the tip was barely touching the surface, and what you started to see magnetic imaging in the face. So in fact, because the sample is so flat, you can do magnetic imaging already in contact. Now, of course, you will have a bit of a topography mix with the phase, but again, the magnetic signal here is very strong and the topography variation is almost negligible. So you will not see a big difference when we start doing this constant height mode. But if you have some topography in the sample, then it is beneficial to do a constant height mode. So the way to do that, I have to stop scanning now and go to the imaging. And imaging modes, line scanning, you do second scan only. And you put a second scan tip lift to, let's say, 80 nanometer. So you see you have only two tiles here for the imaging. So you have amplitude and phase because, well, you scanning at the second height, it's all the same anyway. So you're gonna have image of a constant value. So press start. And you start seeing these magnetic domains already in the phase. Now I did some measurement here beforehand, and so you see these are all nice magnetic images of this tape. One thing to know, if you would like to have a magnetic phase channel as the icon in this gallery, so you have to move it to the left. You have to make it the leftmost tile. So second phase, and put amplitude here. So now when this scan will finish, it will save the file, and then the icon of the file will be the phase image. So because if you measure in the constant height mode, so you might not get much of the amplitude reduction, but all your information is in the phase, so this is what you like to keep. So it will still take 5 minutes to finish this scan, so we will not going to do that. I will show you how the image looks like. Let me start a presentation again. So this is how it would look like in the constant height mode. Well, if you wait these 5 minutes, so that's what it's going to be. And now we're going to see how to do a contour following mode. So the contour following mode is, again, you have to go to imaging, go to line scanning, dual scan. And for the dual scan parameters, you have to enable the contour mode. So here, there you go. And the second scan, you can now reduce it or keep the same. So just make it 50 nanometers. What you can also do, you can change your free vibration amplitude if you would like to have a bit higher XY resolution of your MFM signal. But if you decrease this free vibrational amplitude, so you might lose the magnetic signal. So it's a kind of a trade-off. You either benefit in XY and you lose in magnetic signal quality, or you have a very good magnetic signal, but then the XY resolution is less. So of course, if you do dual scan, you have a lot of these channels. So this 3 dials here are related to the first scan that measures the topography, and the 2 last dials, this is the second scan that measures your magnetic signal. Okay, so let's just start that. Okay, and you can see here the time estimate is about 13 minutes to finish the scan. So that's roughly the double of the constant height mode scan. So yeah, only if you have a complicated sample with complicated topography, then you would go for that. If you just image in films, which are flat and there is no patterning on the film, so there is no reason to use contour following. Okay, so there comes your magnetic signal, or our magnetic signal. So again, we're not really going to wait 12 minutes for it to finish. We can, yeah, I will keep scanning. So while we're looking at how the final image would look like. So this is the final image. As I said, it looks exactly the same because essentially the system is doing the same. So the tip is just going above a certain surface, certain distance above the surface. And both modes, because the sample is flat and the contour is flat, both modes show you the same image. So that is pretty much I would like to stop. And if you have any questions, I would like to answer them, and I will just keep the scanner running. So maybe by the end of it, we will see a full image.
Great. Thank you, Denis. Hope everyone found that interesting, and everyone now knows how to perform an MFM experiment on CoreAFM. So let's get straight to the questions. I'm going to read them out in the order we received them. So if you have a question, now's a good time to submit it through the Q&A tab. I have one question. I think that was already touched upon earlier, but maybe you can elaborate a bit. So in the MFM image, how do you see where are attractive and where are repulsive areas, or repulsive forces and attractive forces measured? How can you see that in the image?
Yeah, I'm going to show this slide again. I talked about it. Essentially, if you have a attractive force, then the frequency shift is negative. So your frequency of the cantilever is lower, and the phase is also lower. So that displays as dark color in our scanning software. And if if you have a repulsive force, then it means that the dipole in the tip and the local field is anti-parallel, so they're facing to each other. Then you have a higher frequency, and then the phase is also higher, so that is displayed as a bright color in our software. So now if I go back to the scanning, so you see there's like darker and brighter colors. So the darker means the attractive forces and the brighter repulsive forces. Now, what is the true orientation of the magnetic field here? So that really depends on how you magnetized your tip. So I recommend getting a magnet on which it's written where is north, where is south, and use this magnet to magnetize your tip. Like this, you would know in which direction your field is pointing.
What should the ideal parameters for free vibration amplitude be?
Well, yeah, it's a good question. So here you could see I'm doing it with 500 millivolt. In principle, this free vibrational amplitude it defines the amplitude of the movement of your cantilever. So the bigger the amplitude of your movement, the further you are on average from the surface. So, but also your signal to noise will increase because you go from the very strong field to very weak field in the different points of this amplitude. So yeah, I would choose it such that this amplitude is the size of your features that you're imaging, right? So because if you are imaging very small features of 10 nanometer, you would like to vibrate your cantilever, let's say same 10 nanometers, so you don't go far away from the surface. Now, how this vibrational amplitude converts into the real size of this vibration, you have to calculate it from the geometry of your cantilever and how long it is. Frankly, I find it much easier to more of a try and error. Like you start with 500 millivolts, see if the signal to noise is good, so you can decrease it, see how the signal decreases or quality of your signal decreases. Yeah, try and error.
Okay, good tip. Thank you. I have a sample that changes magnetization upon application of an external field. Can you do that with your AFM?
So we have, it's not a part of this tutorial, but we have an external field magnetic holder. It's an extra product, so you have to buy an additional holder. Let me show you. We'll try to show you a video of it. Magical. So this device here, it's a variable magnetic field holder. So you put your sample here in between the two magnetic poles, and so this part and this part, this is a hard magnetic steel, and inside there is a motor with a rotating magnet. So essentially this rotation of this magnet will define the field in which your sample is submerged. So yeah, in principle, with this device, you could measure change of magnetization in a parallel external magnetic field. So the vertical magnetic field we still don't have, but hopefully we'll have in the future.
Okay, and that fits into the CoreAFM. Was it quite a large thing?
This is made to fit inside of the ISO stage in the CoreAFM. So we have this anti-vibrational stage where the CoreAFM is sitting on, so it goes inside of the bore, inside of this ISO stage. Yeah, there is a question for hard magnetic materials. Interactions with tip are strong, then the MFM measurements can be correctly interpreted. So I guess it's a question if the MFM measurements can be correctly interpreted. Well, yeah, that is a question. It's hard to answer without seeing the image and without doing a micromagnetic simulation. So of course, the interpretation of the imaging, it always involves simulations. So that in my memory, so whatever we do magnetic imaging, even if we did it with the quantum devices, so we knew exactly the field that we measured. So here in MFM, you measure in phase. So with different sensors, there is a way to measure exactly what is the local field at this point. And even then, when we knew exactly the field, we would still do extensive micromagnetic simulations, and only then we could make any conclusions about what is happening in the material, and if our thinking, the scientific logic is valid. So without the simulation, you cannot just say you see this or that in your measurements. You have to simulate. So this is the answer of your question. So you see there's a bit of a dirt on the surface. I went a bit too close to the surface, so I'm gonna lift a bit, go back to 80 nanometers so the image could recover. Now the second question we have, if you have a multiferroic sample, is it possible to investigate change in magnetic domains by application of voltage with a magnetic tip? So yes, I'm not very familiar with multiferroics, but you could apply voltage to the tip. It's here, you could see it, the tip voltage. So wherever you put voltage here, it just goes automatically to the tip. Or the only thing that you have to pay attention to, that you're using a conducting cantilever holder. So I have a cantilever holder here with me. So this one, this is a non-conductive holder. I don't know if you can see a dot there on the edge, but this dot is black, so it means this is a non-conductive holder. It will not be suitable for this measurement. But if you have a cantilever holder with white dot on it, so this is a conductive one, and there you can apply plus minus 10 volt on the tip. I don't know if you need more with these multiferroic samples, so then you would need an amplifier, and then you have to be a bit careful about the grounding so you don't destroy your cantilever coating with this voltage application. But yeah, the answer is yes, you could definitely apply voltage to your tip. So next question, have you tried those tips on biological systems? Can the hard MFM tip work on soft materials? So again, it really depends on the system you're studying. I guess the easy answer, yes, it can, but it also can modify your soft material. I think here the question is the soft materials like soft tissue. Yeah, so this is a good question. If you're looking for magnetism in biological samples, I guess your signals will be small, so you might need to use hard tips to see anything at all, because I don't think you can do it with a soft tip. The question is if you see anything. Yeah, that is. I did study magnetism, or I heard about studies of magnetism in biological systems with quantum sensors, and even then the signals were very small. So I wonder if that is even possible. But if it is possible, my guess would be that the hard MFM tip should be the one to go for. Another question, why only I gain is set to 4000? Well, in the Z controller, what you see here, it only works for the topography measurement, right? So in this sample, the topography is flat. There is no topography at all. So yeah, in principle, the gain could be smaller or a bit higher. So this is a good gain for this particular combination of a tip and supple. P gain, we see it like very little affects the images in flat samples. Also, it's not a polymer, so it's a film. Okay, polymer, if it's film, is a polymer. But yeah, in this particular situation, just other gains will not do anything. And when the second pass is done, so then the Z controller is off anyway. So whatever these values, they're not affecting the magnetic image. Well, I hope that kind of answers the question. So I don't have any
okay.
I don't have any more questions. I know there is one more question coming. Is there a way to look simultaneously magnetic electric properties of the material such as performing EFM and MFM correlatively? Is that technology out there? Huh. Yeah, that is a good question. Normally we don't do simultaneously EFM and MFM because you will never distinguish this if you have a magnetic signal in your system and then you so it's hard to get rid of it, right? So you cannot cancel it anymore once it's there. What you could cancel the EFM by grounding your samples and doing all this thing, and you could hope that you're measuring a pure MFM signal. But even that, what we see sometimes that electrostatics, even in the grounded samples, if you have different materials, different metals on top of each other, we still see effects, maybe electrostatic interaction. And then what we recommend, unfortunately I don't have it like right on top of my head, but there are ways to cancel this electrostatic interaction by doing kind of combined MFM and KPFM measurement. But performing EFM on the MFM sample at this, in the same time, I don't think this is possible. You could do it on the same sample if you switch tips and you go from magnetic cantilever to just conducting cantilever and do EFM separately on the same sample. You would have to open the system and change the cantilever, but together EFM, MFM, it's not possible. Do we have more? Yeah, there is a. You said the sample is flat. Why the tip lost the surface? Well, yeah. So the sample is flat, but there is dirt on the surface. And what you saw here, that the distance between the surface and the sample was too small. So you see here. Let me just move it a bit. So these you see the kind of dots of dust, essentially what it is. And obviously there were more than 50 nanometers. So here at the bottom, so the sample is flat. But so because I was opening and closing the system and we don't work in the clean room, so essentially, eventually some dust gets into it, and then either you have to scan this place a few more times to get rid of the dust, so the tip would move the dust to the side, so then the image could recover, or you just look for another place in the sample, so then you can have better images.
Yeah, so wouldn't usually happen just in the environment currently. I mean, this is the fourth or fifth time you're measuring the sample, I think.
Yeah.
So yeah, okay.
There is more sample. Does the tip magnetize the sample, or do you do from bottom of sample? Does it matter? No. So here now there is no magnetic. I guess the question is if we do have external magnetic field. So now there is no external magnetic field. The sample was magnetized beforehand. So what you see is just a remnant magnetization of the magnetic storage. So you know that back in the days, people used to store the data on magnetic tapes, the disks. So that storage didn't have any extra, energy to stay magnetized. This data was stored indefinitely. So this is kind of sample we're measuring now. I hope the tip doesn't magnetize the sample. Otherwise, we would see strong artifacts in magnetic signal, and we don't see them. So in this case, the tip does not magnetize the sample.
Good. I think there's no new questions. Thanks for taking over there. The tab just disappeared. Here we are.
Is it necessary to magnetize the tip and the sample, or only one? So yeah. Well, obviously, once you get your tips from the supplier, they have only spontaneous magnetization, whatever it is. So all nanostructured, magnetic things, they're magnetized one way or another. So you have to ensure that your tip is magnetized, the right way and fully magnetized, not just half of it or halfway. So the way we do, we have these bunch of permanent magnets, neodymium magnets, like very little ones, or yeah, I can get a bigger one. It doesn't really matter because the tip is so small. So what we do, we put them on kind of a screwdriver like this. And then when you put your cantilever on the cantilever holder, you just try to approach your magnet, not touching, of course, because if you touch, you destroy your tip. So you just approach this magnet to your tip, say a few millimeter away. You can see it by eye. If you're not certain, of course, you can build some sort of a contraption, but even 5 millimeters, I think, would be enough, because the magnet is rather large, so the surface, so you would think that, a few millimeters away, the field is still homogeneous. So this is how we magnetize our tips. The samples, again, it really depends on what samples you measure and what would you like to see in them. Most of the magnetic samples, they would have some sort of a remnant magnetization. So you could magnetize them again with the magnet, then remove the magnet, you will still have some magnetic structure on the surface inside the sample. If you want to study how this magnetization is changing with the field, so then, of course, you need the external magnetic field generator, and that I already showed. So we have an in-plane magnetic field generator that looks like this. So yeah, there is a software to control it, and you can automate your measurements. So you can just set, okay, I'm going to go from this field to that field with this many steps, and the system will do imaging for you. For the vertical field, we're still developing a similar holder. We cannot do it integrated because essentially all the part that does the magnetic job is here. So you can either get the vertical magnetic field or in plane. So it would have two different accessories. But yeah, at least you should magnetize your tip. Samples most time is not necessary. Is it possible to inject spin current to the material and see how the spin is preserved in the material using MFM? Okay, and measuring spin current induced magnetization. Yeah, so I know these measurements are very difficult. So it depends on what material you inject in the spin current into. what is the, the magnetic polarization of your spins inside of your material after the injection, because, injection efficiency, well, I was a bit out of touch with this research direction, but when I was studying the injection of the spin current, the efficiencies were very, very low. You were lucky if you could get 0.1% of your electrons polarized after the injection. With MFM, yeah, I think it will be a hard measurement. Certainly, you can position a sample here on the stage and attach electrical contacts to it and try to do that. But with MFM at room temperature, I think it's a hard experiment. Again, I would recommend low temperatures and quantum sensors for that rather than MFM. But maybe in low temperature MFM is possible, but not at room temperature.